Simple linear regression is an approach which is going to be taking our first shot into building a basic predictive algorithm. And we will try to predict this quantitative response variable called sales, which we will map out in the form y equals beta 0 plus beta 1 x. Now let's explore what each of these terms represent. Y is nothing but the response variable. So in this case, it is sales. Now, since we are doing simple linear regression, we will only be working with one feature to start with. And that feature is represented by x. You can connect that with the problem that we have been working on. So x can either be the spend on TV or on radio or on newspapers. Beta 0 and beta 1 are the coefficients. Beta 0 is called the intercept and beta 1 is the coefficient of x. Together, beta 0 and beta 1 are called the model coefficients. To create this model, you must learn the various values of these coefficients. And once we've learned these coefficients, we can use the model to predict sales. Estimating the model coefficients. Now, generally speaking, coefficients are estimated using the least squares criterion. Again, this is part of the theory that I've embedded links to, so don't worry about what this means right now. It basically means we will find the line mathematically which minimizes the sum of squared residuals or the sum of squared errors. When we do a prediction, we will actually be making some mistakes. So if the sales was, let's say, $1,000 and we predict $1,050, we are basically making an error of $50. A way to measure these errors, or the most popular way to measure these errors, is to actually use what we call the sum of squared residuals, which means we take the predicted value, difference it or subtract it from the response value, and then square it up. So here I've got the equation written down and let's walk through it. The elements that are present in the diagram are the black dots, which are basically the observed values of x and y. And in our case, it might be TV and sales, or radio and sales, or newspaper and sales. The blue line is our least squares line, the line that we want to mathematically come up with to build our predictive model. The red lines that you see there are called the residuals, which are basically the distances between the observed values and the least square lines. And this distance is represented by the sum of squared errors. So how do the model coefficients relate to the least squares line? Beta 0 is the intercept. And when I say intercept, this is basically the value of y when x equals 0. So this basically means, let's say, we assume x to be the marketing spent on television and y to be the sales. When x equals 0, this basically means that I'm not investing anything on television, but in that case too, my sales might not go to 0. So there might still be people who are organically purchasing some of my products, right? So we need to take that into account. So even when the marketing spend is 0, some sales might happen. So in this case, we need to have a beta 0 component which will have some value even if my x is 0. Beta 1, on the other hand, is called the slope, that is the change in y divided by the change in x. This is the coefficient that basically gives us the relationship between y and x. And again, this is diagrammatically represented below. So what we want to do is estimate the model coefficients for the advertising data. In the first case, we will use stats models, and a way to create a linear regression in stats models is basically to call the OMS method and specify the formula in LaTeX notation. So here in this case, I have the response variable called sales, and then there is a tilde separator which says Sales is the response variable, while everything to the right of the tilde sign will be my features. So in this case, I only consider TV as my independent variable or my feature, since we are only doing simple linear regression. And we pass the data parameter to be our pandas data frame. Finally, we call the dot fit method on the OLS setting to notify that using this data, we need to train our model coefficients. And then finally, I can use the dot params attribute of the output to view what my model coefficients are. So let's run this. And again, as already specified, this runs fast. So we've already got our output, and the intercept in this case is 7.03, and the coefficient for TV is 0.04. Now let's do the same thing using scikit-learn and then finally interpret what it actually means. So in order to do it in scikit-learn, we are basically going to pluck out the X, which in this case will be our TV column, our Y will be the sales column, and after doing that, we actually instantiate an object of linear regression, which is already imported from scikit-learn, and then we do an exact dot fit method, and this time we don't pass the data as a whole, we pass the X, which is our features, and Y, the response. And once that model is trained again, we can individually pull out the intercept and the coefficients. So in this case, again, since the method does not change in theory, we can notice that the intercept and the coefficient for TV are the exact same for both these packages, stats models and scikit-learn. Now let's try and take a shot at interpreting what these mean. So a way to interpret this will be a unit increase in TV ad spending is associated with a 0.047537 unit increase in sales. Or more clearly, an additional $1,000 spent on TV ads is associated with an increase in sales of 47.537 widgets. So note that if an increase in TV ad spending was associated with a decrease in sales, beta 1 would be negative. So now that we have laid out the association rules and the way to interpret this model that we have come up with along with its coefficients, how do we use this trained model to make predictions on unknown data? So let's say there was a new market where the TV advertising spend was $50,000. What would we predict for the sales in that market? We would map out the equation as usual, y equals beta 0 plus beta 1 x. And in this case, our trained model has the value of 7.032594 for beta 0 and 0.047537 for beta 1. And notice X was my spend in thousands of dollars, so I'll only put 50 there. And plugging on this equation, we get a Y value of 9.40944, which is depicted below. So we can basically take this equation along with these coefficients and plug it on any real piece of software which can do the math for us. And finally, we can display our predictions. Now let's say we want to do that on a large scale. So you don't want to predict one data point, but you actually have multiple products on which you want to run these predictions. One way to do it will be to come up with the data frame x underscore new, and in this case we are only taking into consideration one observation, and then we'll do a dot predict on stats models to make the prediction happen. And again, our manual calculation exactly matches the output of stats models predict function. The same can be done for scikit-learn. Again, it has a .predict convenience function, and we just need to pass in our data. So basically what we're trying to say is, if you spend $50,000 on TV advertising, you're expected to have a sales of 9,409 widgets in that particular market.